Chemistry 3101. This is Chapter 9, which deals with alkynes. And a number of years ago, there was an ACS, or an American Chemical Society conference, where I think the focus of the conference was alkynes and alkyne chemistry and alkyne synthesis, or synthesis that involved alkynes. And they were handing out bumper stickers that said it takes alkynes to make a world. Anyhow, you all know what an alkyne is by now because you spent enough time looking at functional groups, right? If we take a look at the molecule acetylene, which is what is represented here, this is just a orbital overlap diagram of acetylene. And you know that in the acetylene molecule, the bonds between the two carbon atoms, we have one sigma bond, right? There's one sigma bond here, which is a result of the overlap of the sp2 hybridized carbon orbital with the sp2 hybridized carbon of the other carbon, and then the s orbital, of course. We have an overlap between the sp2 hybridized carbon and the s orbital on the hydrogen atom. Anyhow, so these are sigma bonds, right? This is a sigma bond here, this is a sigma bond, and this is a sigma bond. But you know that the other two bonds, right, these are pi bonds, right? And pi bonds are formed by the overlap of unhybridized p orbitals that overlap side to side. So we have one p orbital here, and then we have the other p orbital here, like this, overlapping. And you should know that a pi bond is weaker than a sigma bond. And you should know how to draw an orbital overlap diagram like this one. That's something that we covered in Chapter 1. It should have also been covered in your general chemistry class. So alkynes possess a carbon-carbon triple bond, and we're going to see some interesting reactivity of carbon-carbon triple bonds in this chapter. If we take a closer look at the electron density around that carbon-carbon triple bond, and again, this is just a molecule of acetylene, which is the simplest possible alkyne. Since we have those pi bonds between those two carbons, the alkyne can behave as a base or as a nucleophile, which we saw with alkenes as well. Something else you should know is that the bond angle between the hydrogen carbon bond and the carbon-carbon triple bond, that's a 180-degree bond angle. Same thing here. This is 180 degrees. And so the molecular geometry is linear, right? You should know that that is a linear geometry. It can be helpful to make a model of an alkyne. If you have a model kit, it can help you to see that linear geometry. Anyhow, a lot of the electron density in an alkyne is going to be focused in between those two carbons in that triple bond. And you can see that in the electrostatic potential map here. The red denotes higher electron density, and the blue areas denote lower electron density. And so we saw a similar type of electron density between the two carbons in a double bond in an alkene. And so many of the addition reactions that we saw in the alkenes chapter are going to work on alkynes as well. Things like hydrohalogenation, right? The addition of HX, right? HCl or HBr. Hydration, the addition of water across a triple bond. Well, before we get into the chemistry of alkynes, let's talk about where you might find an alkyne in nature. And in fact, if you go back to the alkenes chapter, I said there's many places where we find alkenes in nature, right? Many plants and animals synthesize alkenes and alkene derivatives. The simplest possible alkyne that we can have is acetylene, and I showed you the structure of that a couple of times, right? That's C2H2. So we have 2 units of unsaturation. If you draw, a condensed form, it would look like this, or like this, right? Like this. Okay, and we're going to use acetylene a lot in this chapter. It says acetylene is used in torches in torches. So the reason that we use acetylene in torches is because it burns with a flame around 2800 degrees Celsius. And so if you've ever done acetylene welding, you've used an acetylene torch. Now, more importantly for us as organic chemists, it's often used as a precursor in the synthesis of more alkynes, more complex alkynes. And we're going to do that a lot in this chapter, especially on Friday when we take a hard look at synthesis. What else? It says here, more than 1,000 different alkyne natural products have been isolated. So again, we see a lot more alkenes being found in nature. However, there are examples of alkynes being found in nature, and scientists have found about 1,000 different alkynes, and one of them is this poison here, which is called histrionicotoxin, which comes from the poison dart frog, Dendrobates histrionicus. And so people in South America have used this for years. They basically, I don't know what they do exactly, torture the frog, poor frog, in some way, and put it in a leaf, and then it causes the frog to sweat, and then they rub the arrows, the tip of the arrows, in the sweat of the frog, which possesses this poison. Anyhow, kind of interesting chemistry there. So now you know a little bit more about poison darts, or poison arrows, I guess. Anyhow, let's move on from there and let's get into the nomenclature of alkynes. Something that you'll notice in organic chemistry, if you haven't figured it out already, whenever we look at a new functional group, we almost always start with some kind of nomenclature, right? Because before you can start talking about the chemistry of a certain type of functional group, you've got to know how to name compounds that possess that functional group. The good news is, if you understood alkane nomenclature, if you understood alkene nomenclature, it's not much of a stretch to get to alkyne nomenclature. So we're going to use the same procedure that we saw back in chapter 4 when we named alkanes, but we used just a few minor modifications. Number one, we're going to find the parent chain. When we were naming an alkane, we simply found the longest carbon chain, and that was it. End of story. Well, when we're naming an alkyne, it's going to be similar to that, the rule that we saw with alkenes, that we find the longest chain. However, it has to possess that carbon-carbon triple bond. Okay, you got to have the triple bond in there. Then you're going to identify these substituents: bromo, fluoro, chloro, iodo, methyl, ethyl, propyl, butyl, so on and so forth. You're going to assign a locant and a prefix if it's required, if you have mono, di, tri, etc. For every substituent, you want to give the carbon-carbon triple bond the lowest number possible. Okay, could have even kind of included that in here, but anyhow, we want to give that carbon-carbon triple bond the lowest number possible. We list all the substituents in alphabetical order. We ignore prefixes except iso, cyclo, and neo. Those are the ones that we do include. And then the triple bond locant can be placed either just before the parent or just before the -ine suffix. And if you're wondering what rule number 5 means